And it is a great pleasure today to have a lunch talk from the other side of the world, from Michael Walmsley from the University of Waikato, Hamilton, New Zealand. Michael has been is a chemical engineer by training. He has taught and done research in numerous places across the globe, also in Australia, the US, and Europe, and has also been very active in setting up research institutes in Australia, then later on in New Zealand, the University of Waikato, and more recently, the Ahuora Center for Smart Energy Systems at your university. Thank you very much, Michael, for presenting your insights. We're really looking forward to your presentation.
Right. Well, thank you for that introduction, Martin. I've teleported myself to Lucerne. As just been mentioned, my talk today is going to focus on decarbonising New Zealand industry through process integration and renewable energy integration. So just to be provocative, I've got a map there on the side. It's actually an old map of where New Zealand would be positioned at the same latitude in the southern hemisphere if it was switched to the northern hemisphere. So as you can see, New Zealand is reasonably large, about 7 times bigger than Switzerland, going from about 30 odd latitude to 48. So with that, keeping that in mind, in my talk today, I'm going to talk a little bit about the New Zealand government and some of the initiatives that they are taking to encourage decarbonisation of industry. I'll talk about the centre that we've established that's working on this project. I'll explain the role that we see energy digital twins playing, and then I'll also discuss some of the results, just a few highlights of some of our project aims, and then make a few conclusions. So in terms of government policy, over the last 6 years, we've had a Green Left Alliance that's been very conscious about pushing legislation through that's encouraging decarbonisation. So we've had our Zero Carbon Act bill passed. We have an Energy Efficiency Conservation Authority, which works closely with the ministry to work with industry to decarbonise. We do have offshore oil and gas reserves, but they've sort of stopped oil and gas exploration offshore. And that was really about signalling that we needed to not just rely on gas as the transition fuel, so to speak. There's even a coal ban in 2035. There's an aspirational target of 100% renewables by 2030. And we have a large fund which is being used to incentivize industry to invest in decarbonisation projects. It's called the GIDI Fund, and there's a pool of 670 million that's being used. Another important initiative was the government put aside 31 million euros, so that was 50 million New Zealand dollars equivalent at the time, for 7 years of funding for 4 major research groups to focus on decarbonisation. And so we ended up bidding into that pool, and this was sort of the focus of the government's efforts in this area. They wanted 4 research groups to be working at the frontier of innovation in the energy technology space. They were looking to build research capacity in the energy area and also strengthen New Zealand's international collaborations. And so this is really what has brought me here, is I'm working on that third dimension of improving international collaborations and sharing things that we're doing. So just to sort of set the scene about how we went about bidding for that money and what the focus of our research project was, there's 8 universities across New Zealand, and I've sort of shown them there with the red stars. The majority are in the North Island, where the majority of the population is. There were 3 universities that had expertise in areas that were of interest to the project. So we convinced them to join with us. So the University of Auckland, Massey University, and ourselves pooled our resources and bid for the project. Now, just at this time, I'll just do a little side trip to some interesting facts about New Zealand, just so you can sort of understand who you're talking to and sort of the background. New Zealand was actually settled very late in human civilization. So it's only really 1200 to 1300 AD that the first major settlements started to form in New Zealand by Polynesians. The land area, as I said, is about 7 times bigger than Switzerland. There's 5.1 million people at the moment, the majority living in the North Island. But interestingly, we've got 25 million sheep, 6 million dairy cows, and 4 million beef cattle. So our biggest emissions are actually agricultural emissions from animals. It's 48% of our total emissions. So we do have research at our university going on to how to reduce those emissions in cows. We also have 16 provinces. We don't call them cantons, but you know, you get the picture. We don't have as diversified government with the cantons sort of having a lot of power. Generally, we have city councils and regional councils. So this diagram sort of summarizes the project that we put forward for funding. It had a number of elements to it. Over here, to do with industry and the physical assets, we had 3 research aims shown by aim 1, 2, and 3. Aim 1 was about what's happening in the factory and how do we maximize specific energy or minimize specific energy demand. Aim 2 was about how do we convert energy from one form to another so we can sort of maximize the use of electricity to produce heat. And then thirdly, how do we provision renewable energy resources and make it available in an economic way to meet the needs of the factory? So that was sort of the factory side of things. And in consultation with the industry, we had already process integration expertise over about 15 years. So we were fairly confident that we can put up a strong proposal there. But industry was also quite encouraging that there needed to be sort of this modern element of digitalization. And how can we sort of assist with Industry 4.0? So the idea of adaptive digital twin technology platform being developed along with what we're doing in the plants was decided to be included. And so as we do research in the plant, we're looking at how to develop adaptive a digital twin platform that can be used to assist industry to bring about the changes they need to make. So we were successful, 1 of 4 to win some money. This is sort of some of the students. We've got 11 academics in the program, 2 postdocs across the 3 universities, and we've got about 19 postgrad students, and then there's lots of undergrads. The postgrad numbers are probably going to get to about 25 at the peak. Now, you might want to know where this word Ahuora came from. It's actually a conjugate of 2 Māori words, ahu meaning to fashion and ora meaning healthy. So Ahuora is given the meaning of sustainable industry. So let me just give you a brief introduction about the adaptive energy digital twin platform that we're looking to build, and we are sort of developing it in parallel with the other research aims. So, you know, the word digital twin is a bit of a buzzword. All the process simulators that us chemical engineers have used for the last 20, 30 years, they are now magically being called digital twins. And so, you know, what is the difference between a simulator and a digital twin? Well, we like to sort of view it that it looks like, behaves like, and is connected to a physical system. So a lot of our process simulators never actually connect to things, but they do try to behave like a plant. So process simulators do form part of the digital twin platform, but then we have to build up ways to connect in an efficient manner with the real plant and with the computer simulation that's running effectively. Now, with the energy digital twin, we're hoping to have a platform that can enable industry to build digital twins that can operate across quite a range of decision-making time horizon. So from a control point of view, we're talking seconds and minutes, but as we go all the way through to big investment decisions, we're talking multi-year and multi-decade sort of time frame. And so effective digital twins could operate in quite a range of time horizons. The other thing to think about is that digital twins can be used for operational purposes, but they can also be used for engineering and design purposes. So this slide sort of explains sort of two cycles. One, the operational cycle, where you're looking to take information from a plant, send it to the digital twin, do some clever things with it, and then feed information back to the plant to assist them in how they're operating. And like I said, that time horizon could be quite short, or could be over, minutes or hours or even days and weeks if it's influencing the operating schedule. Now, at one level, we've been doing model adaptive control for a number of years, in the advanced process control. This is sort of trying to take that further and use a more sophisticated model to predict what's happening. Then at the design level, we can build a digital twin that can perform and predict what emissions are doing. And then we can make changes either in the form of redesign, retrofits, retiring old technology, introducing new technology. And then we can investigate what will that look like for CO2 emissions over a full calendar year. Now, what I'm going to show you is a lot of our industries are semi-continuous and non-continuous industries. It's very difficult to predict what the CO2 emissions are going to be if you make certain changes to the plant, because the plants do not operate in a steady manner. There's multi-operating states. And so we've built crude digital twins that have assisted industry in being able to more accurately predict CO2 emissions. The government funding for some of their projects requires that they meet the CO2 emissions that they claim they're going to meet. And if they don't, there's a financial penalty. So that sort of sharpens the pencil on what you're predicting. So now let's just talk a bit more about the research aims and the work that we're doing in those research aims. And this is a lot more factory focused. But just to set the scene, I just want to briefly let you know what our electricity and process heat situation is at the moment. And the first thing I'd like to say is that we have a high level of renewable electricity. So about 85%, a lot of hydro, geothermal, a growing wind and solar amount. Solar hasn't quite registered above 1%, so that's why it's not there. It's probably about 2%, at 0.2% at the moment. But we have 15% coal and natural gas. And there's a lot of pressure for that to retire by 2030, even though some of those assets are barely going to be half of their full life. And so it's a political debate going on as to whether, especially the combined cycle gas, stay around longer. And I think there's some real sense in allowing them to stay longer so we can spend the money elsewhere on other decarbonising initiatives. On the process heat front, we actually have 37% renewables. And that's mainly coming from biomass, black liquor in the pulp mills, and geothermal. So what you'll see is we have quite a bit of forest products and wood processing. And then the electricity that we're using is fairly green as well. But the rest is coal, natural gas, and oil. So those are the ones that we've got to try and do something about. The other thing is where renewables are available is quite regional. So on that map of New Zealand, you see there's a big green circle there. That's where a lot of wood processing is done. That's where a lot of forests are, and that's where a lot of geothermal is. The South Island doesn't have any natural gas, so there's a lot of coal being consumed in the South Island. Now, when we talk about process heat, to convince others that process heat is a significant area you have to worry about, this is some of the information that we had to write into the proposal. So I've got a graph here that shows consumer energy in PJs versus emissions. And so the dashed line is the emission factor effectively for the consumer energy. And when we look at residential, commercial, and industrial, that represents about 57% of our energy, 44% of our emissions. But transport, sort of including international transport, represents 56% of our emissions, even though it's only 43% of our energy. I've included international transport because we do rely upon it heavily in shipping and in planes, and we're going to have to produce fuel in order for that to be maintained. So about 255 petajoules of consumer energy is used for heating, and of that, about 79% is industrial within industry, and the rest is basically in commercial and residential and agricultural. Now, just showing you a little bit further in terms of where the key contributors, what industry sectors. Here at the renewables end, you've got the wood processing and pulp and paper, and then a lot of fossil fuels there in the metals, chemicals, dairy, meat, manufacturing. And over on the right-hand side, I've sort of circled, there's where a lot of the fossil fuels are, and the renewables are down there, mainly in the forest sector. Now, when you look at the number of factories, about 300 of our factories contribute 54% of the emissions. And if you look down that list, there's some similarities to Switzerland. We've got 80 dairy factories, 86 meat factories, and 44 food factories, and 75 wood processing. And when you look at the rest, there's 9 factories that are contributing 46% of the emissions. So these are large sort of plants, chemical plants, cement making and things like that. So, one of the key questions for decarbonisation is how long are some of these factories going to be around? They're owned by large multinational companies. So the methanol plant is living off our cheap natural gas. That is 30 years old. That could well disappear. The refinery has closed down. We're just now importing refined oil. And the steel and the aluminium smelters are often under pressure, and they could well change. The steel one might just be more a recycle plant. Cement and the pulp is likely to remain. So, what's their future? So let me now just talk about work that we're doing in our 3 research aims, and that may well connect with some of you and the research that you're doing. And as I said, research aim is very much about in the plant, how do we reduce heat demand? How do we use pinch analysis and process integration to assist industry to identify the opportunities and then make changes? Now, the key industries that we're focusing on generally are dairy, meat, and food, and more recently, pulp and paper and wood processing. So let me just share with you a meat processing case study that was done by one of our PhD students. This is quite a large factory. The energy consumption of this one factory is the equivalent of 6,000 houses. So the rural town, the small town that the factory sits in, the factory uses as much energy as the rest of the town. So it sort of just gives you a sense of, the magnitude of some of the energy consumption in these factories. So we've got a lot of lamb, sheep, and calves and beef that are being processed, and we're using coal, some electricity, and LPG. So in order to study this, this is sort of something that all the pinch analysis guys can relate to. You know, there's the whole data extraction. Once we've got the data, we've sort of going to try to develop the composite curves and then the grand composite curve, do some total site as well, and then identify the heat reduction opportunities of either extra heat exchangers or potentially heat pumps or a mechanical vapor recompression in some industries. So the student went through this process and got the data, developed the curves. And what I'm showing you here are the grand composite curves for 4 of the processes that are operating. And then there's the total entire site. And what you notice there is there's a pinch point up at about slightly above 85 degrees. However, that narrow pinch point is only focused on the rendering plant. And if we took that off, there would have another pinch point down closer to between 30 and 40 degrees. And being aware of where these multiple pinch points are can help you see where you can make changes to the plant. So one opportunity there in the rendering factory is using mechanical vapor recompression, where you can lift the temperature of the vapor through mechanical electrical means and lift it from, say, 85 or 83 sort of over to now supply heat above the pinch. And so the COP that you would get for that is extremely high. 31 makes it a no-brainer to do this, and it's likely to have a very good payback. Now, this meat processing factory is a non-continuous process, has weekly shuts. And so when you start talking about introducing a heat pump or even mechanical vapor recompression and predicting what are the savings that you're going to get, you've got to do non-continuous modeling in order to accurately do that. And that's where the digital twin could come in. And in the case of heat pumps, you also need to be thinking about storage. And so the idea of heat recovery loops and storage and what that volume is all comes into the analysis. Now, there's another opportunity when we implement the vapor recompression and take that plant out and then look at the rest of the site. As you can see there, you've got temperatures that you're trying to cool down here, and you can lift up and provide heat for the utility there in a sort of a recovery loop sort of setting. And COP there of about 3 is possible. Now, these heat pumps are already commercially available, so you're not really having to do any significant research here to sort of make these opportunities available. Now, once we start going a bit further into some of the higher temperature, then we get into the research need. Are we going to use electric boilers with a COP of 1, or can we try to develop high temperature heat pumps and get a COP of over 2, for example? So, that's a question that we're working on. So that leads me to research aim 2 for the heat pumps. And what we're really talking about here is high temperature heat pumps. So we've done a temperature profile analysis for New Zealand. This is really based on the heat that's being supplied to a lot of the boilers. And as you can see, there's about 50 petajoules of heat that's being needed above between 100 and 200 degrees, and then there's 80 petajoules below 100. So there's opportunities for commercial heat pumps down here, but there's also commercial opportunities here if we could develop a high temperature heat pump. So we have a whole research aim devoted to the implementation of higher temperature heat pumps, how to make them economically available, and also with good COPs. So this is one in particular that we're working on, and it ties in with spray dryers, where we're looking to heat up air to 200 degrees directly, using the water loop, both at the top and at the bottom, and heat recovery from the exhaust air. Now, we're proposing to develop a transcritical CO2 high temperature heat pump. And when we talk about transcritical, just to sort of remind you of where the critical point is on the temperature enthalpy chart, there's the subcritical situation and there's the transcritical. So when we're trying to heat up air, that transcritical range is quite good. And you can take advantage of the temperature driving force and the temperature glide of the transcritical heat pump. And as a result of that, you get a lot better COPs. Now, one of the other things that's driving us to carbon dioxide or CO2 is that there's low toxicity and non-flammable, and it sits a lot more comfortably with the dairy and the food and the meat folks. Now, what are some of the work that we're doing? Again, another PhD student been looking at lots of different cycles. Here's 6 cascade systems. They've modeled the effectiveness of these, and for a number of scenarios, starting sink temperatures and what the source temperatures are, and how the COP changes. And we're also in discussions with other international collaborators on building one of these. Okay, so let me move on to research aims. Got a few minutes left. So in this one, this is where how does the renewable energy supply relate to the factory and be available for the factory? And these are some of the research questions we're trying to answer. Is how much new renewable electricity and or biomass is going to be needed for industry by 2050? Where should the renewable electricity be located? Is there any advantage having decentralized local smart grids, or do we just go with the centralized national grid? And what role can factories play, since they're such big energy users, in enabling local smart grids? And so we've done some analysis around how much electricity increase it's going to be. We think we're going to go from about 42 to 70 terawatt hours. Those are backed up by government reports, but there is going to be coal and natural gas coming off. So we need about an 82% expansion in electricity. This is what's going to be needed for process heat, and there's going to be a certain amount needed for light vehicles and heavy vehicles if we electrify transport. This is another government report that sort of talks about what they predict the mix is going to be. I won't spend a lot of time on this, but it's really just to highlight that we do see solar and wind as the big movers, and geothermal, okay, as being the increase. But, this increase in capacity is non-trivial, and there's going to need to be upgrading of the grid. And so the grid is shown there in the map. So our hypothesis, if we have a more distributed situation, then the grid wouldn't have to be upgraded as much. So just another case study we're looking at is how you could integrate the factory into the community, into commercial and the transport sector, and local renewables. Now, to make all this work, I've introduced the concept of the grid-connected net zero energy factory. So to assist in the promotion of more renewables, maybe government should be considering not just net zero buildings, but maybe net zero energy factories to share the risk of investing in the renewables. So that's a concept that I'm promoting in New Zealand, because there needs to be some risk sharing here. So these are some of the things that we're trying to answer here. Is it possible to be grid connected? How do we keep the grid connection so we don't have to expand it too much? How much thermal energy storage? Do we need grid batteries locally? How do we go about integrating a factory? What's the feasibility of the local demand response? How do we, what's the pros and cons of decentralized versus national grids? At the moment, we have 10% grid losses across the grid. We're going to double in size. We don't want to double our losses. Maybe we can keep them down at 4. And we're doing advanced multi-scale modeling and optimization to do that. And this is the sort of variability that exists in the factory. And this is the variability in the supply. This is solar PV. There's the wind. And we've looked into things like, if you look at hourly balances, this diagram is showing how many hours are balanced. This red line is when it's balanced. As you can see, there's not much balancing going on, but with a bit of storage, we can do a lot better. So thermal storage can do a lot. And this is further illustrated here. You know, thermal storage can sort of help to balance the load and take the load off the grid. And we've developed some ways of sizing the storage here by modeling what happens throughout the whole year. Okay, so just in summary then, I think New Zealand is well placed to be able to decarbonise process heat. We do have a lot of renewable energy options. We are working in the areas that could make a difference. I didn't mention, I didn't have the time, but I do have a PhD student working in the hydrogen space and looking at what hydrogen we need in some of our chemical factories, especially the fertilizers. The energy digital twins can help. And the 3 research aims that we're focused on, we are definitely looking at real industry solutions. And what you are doing here in Switzerland parallels very closely with our thinking and some of the solutions that we're coming up with as well. Thank you very much.
Thank you very much, Michael, for this very inspiring talk. Thanks a lot.